In this lecture, we will start on a new topic on feature matching and model fitting. Let us consider a typical problem where you require this kind of matching of features. For example, you would like to compute the 3D structure of a scene. So, we have already gone through the computational aspects of this particular problem, and we can design an algorithms or computational steps to solve it. So, what we can do? We can get a set of pairs of corresponding points. That is the first thing we should get, and in fact, this is a step where we will see that matching is very much required. But just to give a holistic view of this solution of this problem. So, you need a set of pairs of corresponding points, then you should compute the fundamental matrix, and then we should derive the camera matrices, and then we can solve for 3D coordinates of scene points for each pair of corresponding points. So, you see that your initial assumptions of having a set of pairs of corresponding points, that itself requires some introspections. So far in our computations, we have assumed they are available either by visually finding out which points correspond to what. So, let us consider these particular structures. So, what we can do, at least if you would like to automate this process, we would like to find out first the interesting points in those images as the feature detections we have discussed. So, we can apply those transformational invariant feature detectors like shift detector, Harris corner detectors, and also apply the detections in a scale invariant and transformation invariant manner. So, consider these particular operations where you first you defined a measure like Harris corner measure, and then from there you get the feature locations by finding out the local maxima in this particular out of this set of points, and those points they define your feature points. Similarly, for the other view also you perform the similar operations. So, now since you expect that these points which you have detected, they are transformation invariant, which means even after the change of view in the imaging, still those points will be retained in your after detections. So, there should we could try to find out that what are the correspondences or which point corresponds to the which point of the other image, which means that we need to find out this kind of relationships where a point in the left image corresponds to the image another point in the right image, and their relation is that they are images of the same point. So, you can check with this particular thing. So, we are trying to find out, for example, this point and this point. So, by precisely locating the feature points, we are trying to get a correspondence, and in this way you would like to get the set of corresponding points. So, the computation which involves in pairing these points or getting the corresponding points, pairs of corresponding points, that is what is the which is known as feature matching. So, we will be discussing some of these techniques about this feature matching. So, this is the summary of that computations what we discussed, that first you have to detect feature points in both images, and then you should describe them by local statistics. So, this is the way how these points are to be matched, that just the locations will not give any particular information about the nature of the point. So, you need to at least look at the neighboring statistics, neighboring distribution of intensity values or some functional distributions in its particular neighborhood, and which you are expecting that would also remain similar in the other image of the same landmark point around that same key point, and then exploiting that similarity you are trying to match them. So, you have to describe them by local statistics, and we have discussed about different feature description techniques like shift descriptor, surf, Verbi, different kinds of descriptors, and which have the properties of this transformation invariance. And then you have to find corresponding pairs. So, we will be considering that what computation involves. Suppose you are given those descriptions, then how do you say that this pair of points are the corresponding points. So, we have already discussed in the previous topic also, because while explaining the motivations of describing a key point, that one of the computations that we considered, that matching using this representation. So, same description or same discussions we will be repeating here, that you can represent a key point by a feature vector that we have considered. That suppose we have a feature representation of a vector. Here it is an n plus 1 dimensional vector, please note in my notation, starting from f naught, f1 to fn. And then you can use some distance function to define the proximity or similarity between two vectors. You can, other than distance function, also directly you can use any similarity measures also. So, some of the examples of this distance function are given here, like you can use L1 norm, which is defined in this fashion, that with our representation of feature vector, if you sum the absolute differences of the elements or components of those vectors, that would give you this norm. And similarly, L2 norm is the Euclidean distance between two feature vectors in that particular n dimensional space, so, and which has been given in this particular expression. And in fact, there exists a family of such norms, in general we can call LP norm, where the expression looks like this. As you can see that the value of p, if it is taken as 1, then it gives L1 norm, p if it is taken as 2, it gives L2 norm, and in this way you can define a family of norms. In general, for any value of p, you can define this function as shown in my slide. So, you can use these distance functions to define the proximities between key points, and you can apply certain strategies. We will discuss that later on, that how to declare that two key points, they correspond to the same scene point for an image, for two images. Sometimes distance functions, you can have weighted distance functions, which means in our previous examples of distance functions, we considered every component has uniform weight. We did not distinguish that which component is more reliable and which component is less reliable. So, if it is more reliable, we give more weight to that differences. If it is less contributing to the discrimination of the images, reliable means its contribution to the discrimination between two images. So, if it is less, then we give less weight. So, this can be represented in this particular mathematical form. As you can see that it is a it is used the column vector representation of a feature vector, and using matrix operations you can compute this distance. So, in this expression particularly note that A is a positive semi-definite matrix, and which means that it is a symmetric matrix, and if I perform this operation V transpose A V, that should be greater or equal 0 for all V. So, its value should be positive with respect to the same vector, and typical example of A is given here. So, note that this is a diagonal matrix which we can represent in this form, that we can write W0, W1 to Wn minus 1. You note here that we have considered here feature vector is in n dimensional space. So, W0 to in the previous example we have ranged the index from 0 to n, which was an n plus 1 dimensional space. So, this is the diagonal matrix and all others are 0. So, this part and this part, they are all 0. So, if I multiply, if I use this diagonal matrix here in this expression, then it is simply this expression will boil down to in this form, which means that you will find that every ith component, the difference of the ith component, they are weighted by Wi, where weights are all greater or equal 0. That means weights are all positive. So, one typical example could be that they could be weighted by inverse of the standard deviations of the variations in that ith component of the feature vectors. Say we can consider or variance rather. So, if I consider Wi is 1 by sigma I square, where sigma I is the standard deviation of the ith component of these feature vectors. You consider all possible feature vectors. So, what is the variability on the ith component? And then if it has more variability, we give less weight. If it has less variability, we give more weight to define this distance. So, this could be one such policy by while defining these distances. One typical example of weighted distance function when we can use Wi equal to 1 by sigma I square, and sigma I is the standard deviation of the ith component. If I consider the statistical distribution of the ith component of these vectors. There could be other kinds of similarity measures. So, instead of distances, by distances compute the distance between two feature vectors, means smaller the distance, greater is the chance of having them or declaring them similar, or the smallest distance between a pairs of feature vector may indicate that they are the matching pairs. Whereas, for similarity it is just the inverse relationship, where in a similarity measure the higher the similarity value, higher is the chance that they are matching candidates. So, two such similarity measures which are used here, one is called normalized cross correlation measure and the other one is cosine similarity. So, let us consider their mathematical forms. So, this is the normalized cross correlation measure, which you can see that it is defined as the correlation between two distributions, where here distributions are considered in terms of their components. So, it is covariance of f and g and standard deviation divided by standard deviation of the vector f into standard deviation of vector g, as defined in this particular expression. They have been expanded also in my definitions, and as I mentioned that here we are considering the variability of components, the values of components across the vectors, and we are comparing those variabilities with respect to two different vectors. And if they are very similar, this cross correlation value should be high. Actually, it ranges from -1 to 1. So, if they are very highly similar, then it should be close to 1. Whereas, the other function which is called cosine similarity, that is defined in this way. So, this is the cosine of angle formed between these two vectors. So, we are normalizing these vectors and then you take the dot product, and that defines the cosine of angle formed between these two vectors. So, as you understand here also, if the vectors are very similar, this angle should be near to 0. So, which means the cosine of that angle 0 should be equal to 1. So, here also the values range from -1 to 1, and the values which are very or the vectors which are nearby and which are very similar, there the value should be high. It should be close to 1. So, let us now consider what kind of different matching criteria could be there. So, I will consider distance based matching criteria mostly here, and you can extend this discussion or extend these ideas for using similarity based matching. So, in the distance based matching, the minimum is the distance or smaller is the distance, better is the matching between two vectors. That is the way that this policy is considered. So, one of the policy of distance based matching is that you can use a fixed threshold, which means you can report all matches within that threshold value. So, it is not declaring just a pair of feature vectors, but given a feature vector, it is providing you a candidate feature vectors, and then you may have to do some post processing to select which one is the fittest or which one is the actual feature vector corresponding to the query feature vector. Similarly, but if you would like to precisely define the corresponding feature vector, the nearest neighbor definition is much more useful, because here it is not a fixed threshold. So, it considers which feature vector is nearest to it. The problem is that you need to also consider, that means it does not consider that whether the distance between them is greater than certain threshold value or within certain threshold. You can combine them, of course, but by definition nearest neighbor is the feature vector corresponding to. So, if I say that there are feature vectors, say x 1, x 2 to say x n, those are the candidate feature vectors, and you have a feature vector y in another image, and this is the feature vectors in another image. So, what you are doing? You are computing distance between this each feature vectors and which one is the smallest out of them. So, you take the minimum of them, you know that operation called argmin, and that would give you the corresponding feature vector, that means x I star, that is the nearest neighbor of y. But it may happen that the distance is greater than the fixed threshold what you have considered. So, you can apply that consideration also while selecting this nearest neighbor point. So, this is the strategy when you are considering nearest neighbor principle of detecting of matching a pair of feature vectors. The other strategy, which is found to be more robust, is called nearest neighbor distance ratio. So, in this case it considers the ratio of distances between the nearest neighbor and the second nearest neighbor. So, that means if it is distinctly nearest, that means the next neighbor is quite far away, then we should accept that as a really that is a reliable matching of between these two feature vectors. So, which means this ratio should be very small. It is the distance between the nearest neighbor and the second nearest neighbor. So, ratio should be very small, and if this ratio is small, very small, then you can consider that this is a good matching point. Here also we are not giving an absolute criteria, it is a relative distances, two distances what we are comparing. It is a relative comparison between two distances, one distance is with the nearest neighbor and the other one is with the second nearest neighbor. So, there is a figure by which we can understand this particular process. So, in this example you can see that the feature vectors which are actually closer in the space, they are colored by the same color. So, for example, if I use a fixed threshold of th, then all the feature vectors within this circular region around this state. So, we are showing in a 2-dimensional space. So, it would be sphere if it is a 3-dimensional feature vector, or for an n-dimensional feature vector it would be an hypersphere. So, anyway, so within this region, if there is any feature vector, that would have been reported, but what happened, the nearest neighbor of this one is just outside of this circle. So, if you use fixed threshold, you will be missing this. If we use nearest neighbor principle, then this will be also selected, which means you get a true match according to this particular configuration, and also it matches with the ground truth, as you have considered that they are the true matching points, closest neighbor. But the if I consider nearest neighbor principle, then what happens, you see that for this point, this is the nearest neighbor, but it's not the corresponding matching point. It is showing with the different color in this particular case. So, this though it is nearest neighbor, but still no, it should not be considered. So, that there the nearest neighbor distance rule comes. If I consider the nearest neighbor distance rule, then with respect to this particular point, this is the first nearest neighbor, which means that this is the nearest neighbor, and this is the second nearest neighbor with respect to this point. So, if I take the ratio of between these two, and this ratio is expected to be small according to this diagram, and then also we accept it, which means that even the principle of nearest neighbor distance ratio, which is shown here in the acronym NNDR, even if we apply them, then also it is accepted. Whereas, if I consider the other situation, you can see that here with respect to this image, this point, this one is the first nearest neighbor with respect to this one, and this is the second nearest neighbor. And the second nearest neighbor is also quite close, as you can see, because there is an ambiguity of descriptors in this case. And if I take the ratio D3 by D4, then this ratio is expected to be higher, and then with appropriate thresholding you can consider, you can reject them. So, this policy, NNDR policy, it is also rejecting in this case, and which is desirable, because using nearest neighbor principle, this will be assigned, this two will be matched using nearest neighbor principle, but which is not desirable according to the given data. So, that is why this policy of nearest neighbor using distance ratio is found to be more robust than the other policies. So, we discussed about matching of points, key points using their feature descriptors. What about regions or even the images where you represent a feature description, where you have a feature descriptor in the form of histograms of certain measurable quantity. So, there you require matching of histograms. Now, histograms also can be considered as a feature vector. Each bin represents as a component of a feature vector. So, there you can use usual distance functions, what we discussed in the previous case also, like LP norms could be used and with respect to the corresponding bin, and usually L1 norm is used most for representing these histograms, that has been found, but no, you can use any other norm. But there are other special measures, other special distance functions or measures by which you can describe the differences between two histograms or similarities between two histograms. So, one of this measure is called Kullback-Leibler divergence measure, and it considers, actually it tells you, if I give you two probability density functions, probability distributions, two different probability distribution, how close or how different they are. So, the measure is defined in this way. That means, given two probability density function P and Q, you can convert histogram to the probability density function by normalizing the histograms. Then this is the expression by which you can measure this divergence. There is also another distance function which is called earth movers distance function, and which I will elaborate a bit more. So, in this case the idea is that you have two histograms P and Q, and you consider that transforming one histogram P to Q by transferring masses from a bin to any other bin of Q. So, you are assuming that every bin represents, every bin has certain amount, that is the definition of histogram, it is a frequency distribution. So, frequency is considered, frequency of that particular quantity, that itself each unit is called, each considered as a mass. And if you are going to transfer a portion of that to another bin and of a Q, and so that the histogram P gets transformed into Q. So, this transfer has a cost, and this cost could be defined as the product of transferred mass and distance between bin, which mathematically I can express in this form, that m and the distance between two bins. So, each bin, say ith bin and jth bin, their difference of the bin locations itself could be considered as a distance, that absolute differences between bin locations. So, you take the product of these two, that is what is the mass you are transferring from ith bin to jth bin. So, for example, if we transfer, then Pi, that means the histogram, the content of ith bin, that would be reduced by m, and then the content of jth bin will be increased by m. So, this is the transfer operation that would do, and by doing this thing, what you are trying to achieve is that transform histogram P into Q. So, we consider in this context the total mass of P and Q should be same. So, after doing all these transfers, you are expecting that you can convert the distribution of masses in P in the form of P should be now in the form of Q. So, what is the minimum cost operation, accumulated cost operation? So, particularly this accumulated cost, again it should be normalized with respect to the total transfer of mass, that is the measure. So, what is that minimum cost, and that it will give you the distance, and that is what is called earth movers distance, because it relates, it's like transferring mass is something like digging the earth from one place and placing it to the that amount to the another bin. So, something from that analogy the name has come, and providing you a bit more mathematical formulation of this computational problem, that you consider two normalized histograms, because as I assume that their mass should be same. So, the safest way to start with is that normalize both the histograms. So, their sum of area should be equal to 1, that is the total mass they have, and represent say ith bin of histogram P as small pi and ith bin of histogram Q as small q, and you consider the ranges, there are n number of bins, and the Mij denotes the mass transformed from ith bin to jth bin, ith bin of P to jth bin of Q, and Dij distance is expresses the distance between ith and jth bin, that is the distance between locations. So, the earth movers distance is the minimum normalized work required for transforming P into Q. So, which means you are trying to compute this one. So, this is a optimization problem, that you have to minimize this particular quantity. As you can see, this is the cost of transfer from ith bin to jth bin of a mass Mij, and this is the total mass that has been transformed, that is the normalization part of the work. So, what is the set of transfers that would give you the histogram Q, distribution Q from P, and what is the and out of those possible sets, which one will give you the minimum cost. So, this is what is your computational problem, and since you are dealing with mass, there are certain constraints you need to consider. One of the constraint is that every mass should be positive or 0. So, if there is a transfer, it has to be a positive transfer. Then the other one are your transfer of mass from the ith bin of P should not, total transfer should not exceed the content what it has in that bin. That means, that is the capacity that bin has to transfer masses from that to any jth bin of Q. So, that is expressed mathematically in this form. If I consider, if I accumulate all masses from ith bin, it should not exceed the mass, original mass of that bin in the histogram P. Similarly, then what you are transferring to the jth bin in the finally, so that should not again exceed what is the content in that jth bin, because that is what you would like to do. You would like to transform P histogram to Q histogram. So, you have to ensure that it should not it should be always less than equals, it should not exceed that. And in overall, the transfer of all these masses should be less than the total mass of these histograms, one of these histograms. So, minimum of these two histograms. So, it is actually, considering this framework, is not does not really require that two histograms should have same mass, but in our context we considered that they should have same mass. So, in this case it should be always less than equal to 1, because that is what we have assumed, that total mass is 1 in the normalized histogram. So, this is a computational problem, and I am not going to discuss this computational solution of this problem, which is not within the scope of this particular course. But if you are interested, you can go through this particular paper where a typical solution has been presented, an efficient solution. This paper has been published in IEEE Transactions on Pattern Analysis and Machine Intelligence in 2007, and you can find out an algorithm for that. So, with this, let me stop this lecture at this point, and we will continue this discussion of matching of feature descriptors as well as the other topic of model fitting in this series of lectures. Thank you very much.